Get started. So just for you guys on this side, since my back is turned against, like towards you, just like say my name, snap your hand, something. Let me know if you have a question, okay? All right. So we'll try and get through the whole review. I try not to make it too long because I know sometimes the synthesis problems and such can take quite a while. So we'll try and get through that. I did not include NMR here just since I know you guys had that review with Jacques on Thursday if you went. I am going to be posting some practice problems on that if you guys want me to, like when I post the answers to this. This will also be on the Study Union WordPress site, so you don't have to like try and like take pictures or like furiously scribble down every question. It'll be up there, so you can go check it out after. Okay, so let's go ahead and get started. Draw the Lewis structure of C2H4. How does that go? Okay, and how are we drawing this? Like, I'm sorry? Okay, but what will it look like? Can I just do that? Okay, good. So we'll do and what would that look like if we were doing the like actual electron pairs of the bonds?
Well, you know, like two of them on each carbon go into hydrogen. The two of them on each two are also going to the carbon. So they're sharing 4 electrons between each other. They're sharing, each one is sharing 2 between the hydrogen.
Good. All right, you guys remember that? No, it's been a while. Okay. So now identify. Yeah, so these would be correct for Lewis. Oh, I missed H's here. Okay. They would both be correct. This is generally, like, if they're asking you this, it'll most likely be something like this. The bond line wouldn't even have the carbons or the hydrogens even being shown. Okay? So identify the formal charge, if any, on each molecule below. So let's start with this one. How do we identify formal charge?
Well, I remember something like, for instance, section likes 3 bonds, so they had 4, it had positive 1, it had 2, it had negative 1. So, you know, how about however bonds it likes to have, as that much 0, more than that, what's the penalty?
Okay. Did everyone follow that? Okay. So basically, yes. So let's say like nitrogen likes to have 5 bonds to it, right? So say it has 4 groups of electrons around it, then that would be what? Positive or negative 1? Good. Yeah. So we can do the actual like math behind it so you can see it. So aluminum, well, how many does that like to have? It's a weird one. We can move on to the next while someone finds how many aluminum likes. So carbon, how many does that like? Okay, so that one likes 4, and how many does it have? Good. Does it have any lone pairs? Someone, yeah? Where? Okay, so there. Technically it would have it, but it's not drawn on here. And since we're doing formal charge, like it doesn't have them. So basically, yeah, so it has 3, and it likes to have 4, right? So what do we do with that 3? Subtract it, add it, subtract the 4 from the 3. What do we do? What? Okay. 4 minus 3. Yeah, so that's basically what this is. So this is the valence electrons is 4. The 3 is 1, 2, 3. Those are the bonds. If it had the lone pair, it would be 1, 2, 3, 4, 5. Make sense? So that's what that is. It's the same. It's just like condensed. So that gives us what? Good. So positive 1. Did anyone find how many aluminum likes? 3. Okay. So 3 valence electrons. How many does it have? Okay. And now this one. Do any of the carbons have formal charge?
Well, the oxygen is on the actually for the 3 bonds of oxygen are positive.
Okay. How come? Using the formula.
Well, I don't remember using the formula exactly, but for instance, like ketone, like two double bond O, that'd be neutral, and then if those electrons move up into the oxygen, that would be negative. Put 3 bonds, for instance, like hydronium, it's H3O.
Okay. Okay. So that's a good way. So that's like if you wanted to memorize which ones are like giving you, for the oxygen, what charge it'll give you based off of how many bonds. So that's a good way. But if we're using the same method that we're using over here. Okay, so the valence is 6. 3 bonds, and good. Awesome. So 1, 2, 3, 4, 5, right? And that'll give us a positive 1. Okay? And then lastly, this one over here, how many does nitrogen like? Okay. And what am I subtracting? Everyone gets where that 6 is coming from? Okay. Awesome. Now, which of the following is true regarding resonance structures? Go ahead and read through those options and tell me what you think. D? Okay. Does everyone agree? Does anyone have a question on the other ones? So these are just things to keep in mind whenever you are asked to draw resonance structures. Make sure that you're not breaking any sigma bonds, right? You can only break the pi bonds, or you can move like lone electron pairs. And then the octet rule must still be followed. So we can't have a carbon with like 5 bonds. Okay? Now this I just thought was going to be handy for you guys for the geometry. Can you guys see that okay? Is that okay? So this is in terms, oh, never mind. Hold on, we're not here yet. I forgot I had a backside to this page. Okay. So now we're going to use this to answer questions 4 and 5. So number 4 is identify the hybridization state of each carbon. So we'll start over here. What's the hybridization of this one? Okay. This one right here. Okay, good. So this one's also sp3. And this one here? Okay. Does anyone have any questions on identifying that? Okay, good. So now order the bonds being pointed at from least to greatest strength. So, I'm sorry? Okay, so this will be our strongest. Awesome. Everyone gets that? Okay, how about the decreasing length? Okay. So those make sense to everyone? Okay, good. So now we fill this in. So this is just how to determine whether something's tetrahedral, bent, trigonal planar. Okay. This one here? Is that what you're saying? Oh, yeah. So here it's. Let me figure out what I was trying to ask here, because I blanked out the boxes. So.
It looks like the last one's blank.
Like the what?
It looks like the last one's blank.
Okay. Okay. Cool. So here we'll do. So you said this is tetrahedral. We'll just do the bottom ones. Is that what you said? Or did you say another one? Okay. So do we all agree with that? Okay. How about this, if we have one lone pair? Okay. Do y'all agree? And then this one? And then this one, you said? Linear? Okay. Good. Awesome. So predict the geometry for all of the atoms except for hydrogen. So what's the geometry for our nitrogen here? How what?
That one's the SP3, right?
Okay.
So we can kind of, like these first ones, we kind of see what SP3 says.
Okay. So do you guys remember it? If it's sp3 and it has one lone pair? Good. Awesome. And then this one? Okay. Do y'all agree with that? How about this one? Good. Trigonal planar? Okay. And the last one there? Good. Are we all comfortable with that? That'll probably... This is also trigonal planar. That'll most definitely be, if you're in Dr. Dowdy's class, it'll be a question for sure. He likes to go back to that stuff. Okay, so identify whether each of the following has a dipole moment. So for this first one, what do you think is like the best way to figure out whether something has a dipole moment or not? Try it out. Good. And what'd you say? Okay, so yeah, we have an electronegative atom here, right, with our oxygen. But then we want to see, so we have a CH3, CH2, and an O, right? And how do our lone pairs around that O look like? What do they look like? On the oxygen, yeah. Good. So what do they do? Good. So they like kind of even it out. So that'll be what? Geometry. Okay. Good. So then how about for our CO2? What does CO2 look like? For which one? This one? What do you think?
Well, like in the previous example, the O has two like bonds and then two lone pairs. It's like multiple lone pairs.
Okay. So what does this look like? I mean, well, here, let's think about it. So we can actually go back here. So we have two lone pairs on the oxygen. So where does that correspond to? if we have two lone pairs? Bent, okay. And then what about linear? Do we have any? No, basically, so that'll just be with SP, right? So yeah, you're right. This would be bent. So because it doesn't have, and then you would just draw them up here, drawing this. Oh, you can't see that. Okay. And then drawing this way, the bonds to it like that. Make sense? Okay. So then, how about for this one? It's okay. So we have. So now, what's the hybridization on this carbon? SP, okay. And what does that? What's the only one that SP does? Okay. So which one has a dipole moment? The CO2 has a dipole moment? Okay. So this one here, right? Because it'll do something like this. Whereas this one, they'll just cancel each other out. Make sense? Okay. Now arrange the following in order of increasing boiling point. What do we need to look at when determining? Okay, so we have hydrogen bonding. What else? Okay. Size of the molecule. Branching or not. Okay, good. So based off of that, what would we say is our weakest has the weakest boiling point? 1? How come? Okay, but when we're looking at branching, well, we need to look at our intermolecular forces, right? So we have hydrogen bonding. What does branching, what does that affect? What intermolecular force does that affect? Dipole? Good. So the London dispersion. So the ones that basically that are between every single atom, right? So if you had these stacked on top of each other, would that have more intermolecular forces or less than these stacked on top of each other? So this would have more? Okay, good. So then would this have the lowest boiling point? What? Yes? No, okay, good. Yeah, so this would not have the lowest boiling point because you'll also have to think of that one. That's like between everything. So the more linear it is, the higher the boiling point.
I thought it was the opposite.
Oh, okay. Oh, I see that. Yeah, because it looks bulkier. I'm sorry? Exactly. Yeah, so the more surface area it has. So then, now, keeping that in mind, what can we say has the lowest boiling point? And then the next one. And next. Done. 4. What if I took this molecule here and instead put this oxygen between these two carbons? Good, yeah, because it's lacking what? Awesome. Now, what's the definition of a Bronsted-Lowry acid? It does what?
I was saying that acid donates and the base itself.
Okay, so an acid donates what? Okay, do y'all agree? What is an electron donor? A Lewis base? Good. Proton acceptor? Lewis acid? Bronsted-Lowry. Bronsted-Lowry what? Sorry, okay, base, good. And then electron acceptor? Okay, good. So is everyone comfortable with that? Okay. A more acidic proton is one that can be removed or cannot be removed or bonded to a carbon or bonded to an atom with low electronegativity. I'm sorry? A, can be removed most easily. Do you all agree with that? Okay. Does that make sense? Okay. Good. And what would make something, like why would it be easy to remove? Okay, because it has an electronegative atom which does what?
I know, like, you know, if there's more like resonance stability within it, you know, then those electrons can like go here, which is here.
If I have something like this, though, versus something like,
The second, right? Because the first is more electronegative.
so this is more acidic? Would it be the inductive effect?
It's not an alcohol, it's just a hydroxyl, like OH. It dissociates in water easily.
Okay.
If you have an electronegative atom and it pulls the electrons from the carbon, then the hydrogen just falls off really easily.
Okay. So how about, this is what we're going to do. Sorry, I really didn't want to have to do this, but let's just try and like keep it a little more organized of like just raise your hand if you have the answer. I'll look back at you guys too, just so there's not like 5 answers at the same time. So why would this be more acidic?
Which one did you point out?
Oh, sorry. Hold on. Why would this be? Yeah. Why would this?
No, it's OH. I just didn't see it.
Yeah. Oh, I'm sorry. Okay. Okay. So, yes.
Okay, so I think that the proton that's like more easily removed is going to be from CH3 because you don't, because the OH is more, the oxygen is more electronegative, so it's trying to break in the hydrogen atom, whereas the other one, you're going to still.
Okay. Can I hear what you have to say?
I was going to say that it's using the electron rather than the proton, so the proton gets removed easier than the electron because the OH is more electronegative.
Awesome. Yeah, so that's how you want to think about it. This will be removed more easily because remember when we went, like when we did that Lewis, was it the Lewis acid that we, Lewis structure that we drew, and how you have the like electrons between them. So what O is doing here, if this is removed, it's drawing those electrons anyway from the proton, so that proton can more easily just leave or like dissociate. Okay? So does that make more sense? And it's because what's the conjugate base of this?
Water. Is it hydrogen?
O negative. Good. So O negative, right? Okay, so which one stabilizes a negative charge better, this or if we put this? Good, so the O negative stabilizes it more. Why? Awesome. So does that make sense to everyone? No? Or yes? Okay, yes. All right, good. So now, applying that, which direction will equilibrium go in these reactions? So what are the things we want to look at? If anyone remembers the acronym. Yes? Awesome. Good. So we'll look at the conjugate base. And then you said the acronym, what was it? Good. Okay. Which stands for what? Does anyone know what the I is? And the O? Orbitals. Good. Do you guys know what that means? You want? Okay. So what does the atom mean? Like what are we looking at when we look at the A part of ARIO? Of what?
The atom that the H is bonded.
Awesome. So the atom where our acidic proton is bonded, right? So that's what we're looking at there. Resonance, I mean, that's kind of self-explanatory. Does it have resonance or not, right? If it has resonance, is it a more stable base or a weaker, or less stable base? What? More stable, good. Okay, an induction, what do we look at there? Of what? What atom? Is it the atom bonded to the H? So we're going to be looking at atoms not bonded to the H. An inductive effect, remember, if you recall, it's when you have like the electrons being drawn away from that negative charge. That's not the atom itself with the acidic proton. Does that make sense? Does that not make sense to anyone? Okay, so we're good? No? Okay, so basically if we have another electronegative atom, so something like this we could say, just looking at this one example, if this pops off, we're not looking at the inductive effect of this. We would be looking at if it has a dipole moment. So you want to kind of like associate it with dipole moment to where it would be pulling that charge away. Okay? Cool. And then orbitals, what do we look at? Okay, good. So yeah, SP, SP2, SP3. So basically how much S character it has. He always likes to ask the question of a triple bond has more blank, like, you know, his like fill in the blanks, has more like blank character than a double bond, making it more or less acidic, and you have to like decide which one it is. And that's because how can you associate S character with acidity? Okay, how come? Awesome. So more S character will make it hold on to those electrons better. So now that we have that, which direction will equilibrium go? What do we need to look at? You think it goes in the forward? Of which one? Yeah, let's just kind of, no, that's okay. Let's just go like one step at a time. So when we're talking about ARIO, what does that tell us? Are we talking about the acid or the conjugate base? Good. So we need to look at the conjugate base because this all tells us stability of conjugate base. And a more stable conjugate base means what about the acid? Stronger. Good. So what's the conjugate base of this one? Which one? Yeah, so this one here, right? Okay, and then the conjugate base of this one will just be this one, right? So these are the ones we want to look at, right? So atom. Does our atom differ between the two? It does? Where does it, remember what atom we need to look at for that part, the first part. What atom do we need to look at? Good. So the one that was originally attached to the hydrogen. So the one with the acidic proton. So these two are both nitrogen, right? So we can just, that's not going to tell us anything, right? How about resonance? Yes. Okay. Good. And what, here, let's just draw this out. So now we have this versus this. What does the resonance of this one look like? So this double bond goes here to make a double bond here. And then nitrogen will now have, it'll have 2 negative. Because remember, it already has a negative, right? So where does the resonance go? Good. So it'll look like this. Okay? Make sense? And then how about this one? Good. Same thing. So now this one has this resonance structure. And this one has this resonance structure. Now what can we look at here? Now what has a negative charge? Good. So our sulfur and our oxygen, which one is going to stabilize that negative better? The oxygen? The S? Why the S? It's more electronegative? It's bigger. Good. So when we're looking at, because now we can look at the atom part again, like when we're looking at resonance, right? And when we're looking at atom, what do we look at? 2 things. The size and, or, it'll be or. When do we look at the size? When they're in the same what? Good. So when they're in the same group, we look at size, whereas when they're in the same row, what do we look at? Electronegativity. So O is more electronegative than sulfur, but we're looking at the atom part of it now. So we can look at size. So this is going to stabilize it more, telling us what? Which one's the stronger acid? This one? Okay, good. So this is our stronger acid. And our equilibrium goes in what direction? To the left. Good. Awesome. Did that make sense? Any questions on any of that? This is, just a heads up, this is a problem he really likes to give. Something like this, where it's resonance that you can't see right away. Normally you can like just kind of pop the H off and then just look at it how it is. But you have to actually work with the resonance in this one, and he likes this one, so keep it in mind. So how about for this? What are we looking at now from Ario? Good. So the electronegativity of the atom. Why resonance? Do you see resonance on here? Oh, okay. That's okay. So, all right. So we want to look at the atom, right, and the electronegativity. So which one of these stabilizes it better? O. Okay. Awesome. Yeah. So we have N and then O, right, in the same row. So in what direction will this go? Forward? To the left? What is this? Is this is well, first off, is this because we need to look at the acid of the when the oxygen has the acidic proton, right? So what is this? The conjugate base, right? So this conjugate base is more stable, right? Meaning that it goes in what direction? Right, okay. Is everyone on the same page now with that? Okay, good. And finally, this one here. Are we looking at the atom? No, why not? Same atom, good. Okay. So what does this one have that this one doesn't? Or I mean this one, yeah. So this one has resonance, right? So then which one's the more stable conjugate base? This one? Okay, so more stable conjugate base, making what our stronger acid? This one, awesome. Does everyone feel good about that? Okay, good. So now identify the functional groups in the following compounds. So let's do the hand raise for this one because there's several. So yeah, what's up? This one here? Okay, so we have an amine. Awesome. Amide here. What does the amide have? Good. Here? Would you guys say that's an ether? Do y'all agree? Okay. I'm sorry? Your favorite? Oh, okay. Anything else? Phenol, good. And how do we spell that phenol? And what else? Y. Good. And what do we have here? Is this an alcohol? Good. Awesome. Fantastic. Yeah, so this will just be phenol, not an alcohol. All right. And then what do we have here? Do y'all see that? Carboxylic acid. Okay. Everyone good with that? What kind of amine is this? Why is it secondary? Okay, or it's bonded to two R groups, right? So secondary. Someone said what? I think someone said it back there. Good, yeah, so we have an amide. Because remember, an R group, like if you study your functional groups where it says like N, R, R, and R, something like that, an R group can be an H or a carbon group, right? So just keep that in mind. Okay. Oh yeah, thank you. So we also have a phenol. Now, can you guys see that okay? I know it's pretty small and light. Okay, so now let's draw the resonance structures. Well, actually, before we get to that, I just want to show you guys something. So this is just a handy thing that I found. This is from the Klein textbook, but it kind of gives you a real quick overview of what how resonance structure patterns work. So if you have what's an allylic lone pair? Okay, good. So it'll be adjacent to a carbon that's participating in double bonding, right? So that'll be allylic. So if we have an allylic lone pair, that's when you'll have the two curved arrows. Can you see why? Okay, so it's more stable because of that. But then why are we doing two arrows for an allylic lone pair? Awesome. Yeah, so we are going to move it over, and we actually have somewhere to move it over to. And then you can just kind of look through those. If you have any questions, let me know. But that'll help us with the resonance structure forming. Are we good? Okay. So now draw the resonance structures for the following compounds. This one has a positive. So what can I do here? So like that? Starting an arrow like that? Can you see that? Okay, good. So like this, and then from here to this bond? Good. What kind of lone pair do we have here that we're working with in the first one? Awesome, yeah. So we have an allylic, which we just discussed, has 2 arrows. Do you guys see why that's allylic? Okay, good. So then the resonance would just look like this. How about for this one? Is this also allylic? Why not? Yeah, so that would be a vinylic. That'd be a vinylic positive charge, but. So this one moves up here? Okay. And what, anything else? Or is that it? Can we do anything else? Okay, putting 2 double bonds, so a double bond here and a double bond here, and then our O with a positive. Okay. Is this going to like that? Yeah, not really, right? So so we would just leave this like this. We only have to do one curved arrow. So now we have make sense? Our carbon likes that positive charge a little more than the oxygen, right? Good. Any questions on that? And now naming. So what do we need to start with? Okay, otherwise known as parent chain. Good. Okay, which is what in this case? Where do I start counting from? Right here? Okay. Do y'all agree with that? Awesome. And what are our substituents? So here, so first, what is that called, that parent chain, if we have 10? Decane, good. And our substituents, what do we start with? For ethyl? Okay. Why with ethyl? Good. And then what? Does our die factor into the alphabetical? Good. So our die, try, that stuff will not factor in. What does factor in? Okay, but what else? ISO, what else? TERT. Yeah. That's a good question. I would say in that case it might be more of like the if like a cyclopentyl, if it were like a substituent, if that would be alphabetical. I would.
Yeah, it is. Because exam one.
You have to start. You have to like you have to factor the C because it's not a cyclopenicol.
Yeah.
Okay.
Exam one, cyclo comes before everything else. But I got that wrong.
Cyclo comes before everything else. Okay, so it's alphabetical, yeah. Okay, awesome question. Good job. So for ethyl, 3,7 dimethyl. Okay. Oh, I didn't leave myself enough room. Six propyl decane.
Yep.
Do y'all agree with that? Okay. Awesome. How about for the next one? Awesome. So just straight across, and how many, or well, where do we start numbering actually?
The one.
Why?
Because then you'll have the four.
The lowest substituent?
Yeah.
Good. 11? Is that what you said? Did someone say 11 or did I just hear that?
I'm saying I think there's 11.
Oh, okay, okay.
We were just trying to figure out what 11 is in number form.
Indec, is it? Are you looking it up? Okay, good. Yeah, we can. So yeah, I don't think you need to know up to that. I think decane is like the most you need to know. So, yeah, that's 12. So we can add another carbon and call it dodecane if you guys want. Let's do that. Okay, so 12. So undec. Oh, okay. So it'll be UN decane. Okay. So we already added the 12th one though. So dodecane. And what else? What do we start? Like, so we have an iso here. Iso, and then what do we have here? Sec. Good. So for what? And then okay. Is everyone good with that? Yeah, so those will be included in the alphabetical, whereas di, tri, and stuff will not. Yes. Oh, that's a great question. Yeah, so that would be a chirality center. Yeah, so then, so what would we add at the beginning? This was from the like alkanes chapter, so I didn't have that yet, but yeah, good point. So what's our 4? Our 4th carbon. Is that R or S? Why not? Are they the same? Yeah, good. So then which of these has higher priority? Why? Awesome, yeah. So you want to go like one at a time. So here we have a carbon bonded to 2 hydrogens. Here we have a carbon bonded to 2 carbons, right? Good. So then what does that make this RS? S. Okay, good. Do you guys see why? Does anyone have any questions on that?
Is that because like all the bonds change first and then iso?
Yeah, so here we have a carbon to a carbon to a carbon to like all that stuff. Yeah. So,
Iso is better than non-iso.
yeah. Yeah. I see what, yeah, I saw that. So you have, if we're looking one carbon at a time as we had to do here, then it would be what? R, yeah. Yeah, so you want to look at one carbon at a time. Glad you caught that. Okay, so then how about for this one? R? Does everyone agree on that? Okay, cool. So then how do I show that at the beginning of the name? Seven starts with an S. I was close. Okay. All right, we good there? All right? Yes. Is it B? What did we say goes, like, does count alphabetically? Where does it say that?
This one doesn't count. This one, it comes separately. You still will count the B.
Based off of Dr. Dowdy's, it does count. So sec, ter, and iso will count alphabetically. Yeah. So that's why that's, and yeah, you're right. It is like separated here, but for the sec and the tert, but it's still counting alphabetically. Okay. So then, how about for this one? What's our parent chain? Hexene? Hept? Okay. Could we quiet down just a little so I can hear like the answers? Thank you so much, guys. Okay, so we'll do heptene, right? And where do we start numbering? Good. What if I added, or what if I had a triple bond here? So this is still in the middle, right? So if I had a triple bond, where would I start numbering? Still at the double bond. Good. So keep that in mind. It feels like it would be the triple bond, but the double bond will be the first one you start numbering from. Okay? So then we have our heptene, and what does it have? Good. So four, tert, butyl, and then good. So, and then how about, does this need anything or are we good? We're good? If it starts with 1?
Well, I'm seeing it too when
Yeah, it fits in a cyclo. Yeah, for the linear ones you do.
I think I've seen it too where they'll do like hept-1-ene.
Yeah, that works as well. So if you wanted to do the hept-1-ene, works too. But yeah, so if it's a cyclo, you know that that'll be on your number 1. For this one, you don't actually, if you don't show it anywhere, like if you were just given, you have to kind of think about it in terms of if I'm given 4-tert-butyl-heptene, do I know where that ene is going, right? So if you don't, then make sure to number it. Yes?
This online, the review.
I will post it online after this. So now for this one. Hexine. And where do I start numbering? Left or right? Okay. So that's the other naming you can do of like the dash in the middle. Okay? Any questions on the naming for that? Okay? Yeah, what's up? Great question. So what do E and Z mean? Like what do they refer to? Good. So it's like cis or trans, but why can't we say it's cis or trans? Good. So cis and trans have to be the same groups, whereas E and Z means what? If I had, so I'll do, I'm sorry? Good. So if I have, if I have this, what is this? E, oh, you guys can't see. Okay. E or Z? E? Okay, so we can do cis here, but what about our priority? E, okay, good. So it'll be cis and E, so that kind of tells you E and Z aren't always going to be cis and trans. Like some people like to think of Z as that's cis, but that's not always going to be the case, yes. Why is it trans? Yes, can you answer it? Yes.
Okay, question. I don't know if you guys this. Didn't you say in class that it can always be C and Z though? You said you're trying to take an example.
You are if you don't know for sure.
I don't know.
Okay. So yeah, in that case, use E or Z. But then how do we show that, like, why is this E? What are our higher priority groups? So on our left, what is? Carbon, because here we have a hydrogen, right? And over here, chlorine. So if you were to draw a little plane between these, are they on the same side or on different sides? Yeah, okay. So different sides. So same side is like what he likes to say. So if it's Z, they're on the same side, right? Okay. So does, yeah.
I thought like cis and trans was like planar, like sticking above the plane, below the plane, rather than like same side. Because that's cis and or sin and anti, right?
Okay. Yeah, so for this, like with these cases, like when it comes to naming, well, you wouldn't ever name it as sin or anti.
Oh,
yeah, so this is like for naming.
Yeah, okay.
Yeah, so that's like when you have two groups that are on the same side. You can still use cis or trans. It would just be cis here. Or you can use E. But that's why we're not calling it trans, because they're not the same here, but we can call it cis because there are two. If I had something like this, if I instead had an ethane instead of or an ethyl instead of a methyl, then could we use cis? No, we could no longer use cis. Whereas here, we can use cis. Yeah, but you could still name it as cis. If it was,
The same group between all three?
Then no, you wouldn't really need to consider that.
Could that even happen?
that,
I know, but now I'm just questioning. What if there was just a method?
yeah, instead of the chlorine,
Just that would be considered.
but then it'd be both. I see what you're saying.
So you couldn't use it.
I would say you just, yeah, I don't think he'll ever put that, and yeah, he wouldn't just, okay, all right. So with what we have here, are we good? Yeah. Yeah, so you can't name it like cis, blah, 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 E, blah, blah, blah. Like you would just name it one or the other. Good. Good point. Okay. So draw the Newman projections for the following, and the arrows are showing you where you're going to draw it from. So how do we draw our Newman projections? I'm sorry? Good. So if you don't know where else to start, just draw a circle. Okay, we have a dot in the center. And what does that dot show us? Good. So the first carbon we're looking at. To the top? What side? Good. So top right. Oh.
No, wait, I think it's the top left.
Yeah, yeah. Wait, what? Top.
If you look at it
Top.
this way and it's coming out the page and you turn it.
Yeah, it's to the right. Yeah. So the way you want to look at it is you're kind of like taking this molecule, taking it, so say it's laying down, right? And you'll just take it, flip it off the page, and look at it. So did everyone follow that? So for Newman projection. So it's laying down, take it, pick it up. So when it's laying down, it's sticking out of the page, right, because we have a wedge. So when we stand it up and look at it this way, where is it going? To the right. Good. So we have that, and then what do we have on the left? Good. So we have a hydrogen, and then what do we have at the bottom? Good. And now what?
To the other one, you got bottom left, chlorine, and then bottom right, hydrogen, and tippy top, methyl.
Does everyone agree with that? Does everyone feel more comfortable doing those? Do you feel good about? I know that's a struggle area for a lot of people. No, you could just draw it, like draw the line. So how about for this? Start the circle. Okay.
And then dot,
I'm sorry?
and then the dot.
Okay. Ethyl down. CH, so this CH3 to the left, to the right. Good. Because remember, we're, again, taking it, now we're looking at it from here. It's down. It's sticking out of the page. We flip it up. It's still to the right. Do you guys get what I mean when I say, like, flip it out of the page? Okay, good.
The other way, right?
It's because you want to flip it the way that you're looking at it. So because you're looking at it from that direction now, you're going to turn it like that way. Yeah, exactly. Oh, I put R. Okay. So methyl.
Well, I think the top circle, you're gonna have that, what's the propane? Wait, I mean the ethane.
The top one, oh, so you're saying like, it's going to go where, sorry? To the,
Well, the dot, I mean, the circle then would be the one going this way.
yeah, so this will be the carbon on the other side of this circle, right?
Yeah.
So then,
Have the ET on the top.
good,
And then how's the flame?
awesome. Does that make sense? Okay, awesome. And our last one? Methyl up? Is that what you said? Okay. Good. Do you guys feel like you can do Newman projections pretty easily? No? I heard some no's. You got it. It'll just, with practice, these will look much easier to you. So now the reverse of that, draw the bond line structure for this. Okay, so we have this CH here, and then where are the chlorines been going? I mean the methyls, yeah.
Well, one's on the plane and one's going backwards, so hash, right? Because like if you take it like this and flip it back that way, one of them will be going into the plane.
Okay, so you're saying something like this and the other one like this?
Yeah.
Okay.
And then you don't have to draw that.
So if we're looking at it, because we're looking at it from this direction, right?
Yeah.
So we're flipping that, and that'll give us a CH3 at the top and the CH3 on the left. Do you guys see that? If you don't see it, don't worry. We can like take our time through it. Does that confuse anyone? Okay, cool. So then what does our back carbon have?
Draw a carbon on like choo-choo, or that's like, on the plane. And going out, you got another, on the wedge, you got the ethyl again. And then going in, you got that ethyl. Yeah.
So you're saying like that?
Yeah.
Do you guys agree? Not for this, because this you do need to show that that's why. And honestly, no, for neither. You need to draw those for this. Yes? You could do that. Yeah. Okay. How do you guys feel about that? Newman projections? Good? Okay. So now arrange them in order of increasing stability. So from least to most stable. Okay, so we're looking at the, we want to look at the hindrance that's happening, right? So then which one has the most hindrance? The last one. What does it have? Good. So it has torsional strain and what? Good. So this has both, making it very unstable, right? So actually I'll number these just to make it easier. So 6, and then what next? Why 2? Yeah, so staggered will be more stable than eclipsed. So first you want to look, so we want to get rid of first all our, the eclipsed ones, right? So our eclipsed ones are number 6, number 4, and number 2. So,
So then two, two and then probably two, then four.
yeah, that's a good question. Why is 4 good? Okay, good. Yeah, so that's what you're going to want to look at. It'll be what you said. So in this case, it'll be the 3 is the same as 4, but 4 is eclipsed. So it's just like rotated. Yes. 2, yeah. So that's what I'm trying. So this one, on the other hand, is like number 1 because you need to rotate it. So because remember, eclipsed means they're actually like on top of each other. It's just like shown like that so you can see it. So this is here, but if you were to rotate it to make it into the staggered, this would be the same as number 1. Good. Do you guys see that? Did that make sense? Yeah. Yeah, so this is lined up with the hydrogen here, and if you were to just make it, like these are the same. So if you were to just make it back into staggered, it would make it so that it was closer. Now it has the steric hindrance as well. Yes.
My apologies. When, like, if we do this in the line bond, how do you know which one is behind and which one's in front of the memory projection? Do we just choose? Like,
The
say if we
one,
wanna put one
okay.
right here?
The one in front is always the one that comes off of the little, like, triangle thing here. Yeah. Good question. So after 4, what's next? Five, 1, 3. Okay. Now. Okay. 5 and 1. Yeah. So that'll just be like the probably like enantiomers or something. I don't know what this. Yes.
I'm sorry, I know you just explained this. I don't understand why 4 is that unstable.
Okay. So 4, it's actually, so this is wrong, just FYI, because we said what about the staggered versus eclipsed? Good. So eclipsed is going to be, because torsional strain is going to have a big factor in whether it's stable or not. So then how would we rearrange this? Let's just get it right, and then I can like answer the questions on it.
I would have put 3 as the most stable like that, but then I would have had 4 as a little bit less than that. Like I wouldn't have had it 4 be that unstable. I thought that 3 and 4 were kind of.
So the reason that 4 is unstable, so torsional strain makes things really unstable. So it is going to be the, what is it, gauche, right? If it's opposite, yeah. So it'll be on the opposite side if you were to rotate it to where it's not behind it. But because it's not that way, like you have torsional strain. Like you have 2 groups that are like laying on top of each other. Yeah. Yeah, exactly. Four is less stable than 5. 1 is more stable than 5. Oh, yeah, it wouldn't be. They'd be the same. So it'd be like, yeah. So just look at the torsional steric strain and look at whether it would rotate, or like when it rotates, if it's gauche or what's the other one? Or what? Okay, good. Yeah. Awesome. So now let's draw onto chair conformations. Let's draw the most stable chair conformation. Okay.
B would be like equatorial, right? Because like that would definitely be more stable.
The BR?
Yeah, yeah.
Okay. Which equatorial? Upper or, well, what does that look like?
Well, it looks like it's on the tip top of it.
More on a slant.
Good. Okay, so it's at a slant. So where can I put it? Okay, on any carbon. Good. And how many carbons away? So yeah, 1, 2. So it'll be here, right? And then what does that mean? The fact that they're both on wedges. Okay, so we have to draw it down, which would be going where? Equatorial or axial? Oh, or like, so these are always down and these are always up? For axial. Yeah. So those are, yeah, you're right in that. So for axial, these are always up and these are always down, but for equatorial. Yeah, good. So then this will go down. So is this our most stable conformation? Why? Good. Yeah, so they're both equatorial. I don't know if for this one it would do it, but if it were the case that one needed to be axial and let's say this is trans instead, or not trans, dashed, then good. So we would want our BR still to be equatorial, right, to make it our most stable. And then this would just go up. Okay?
So that would be axial up.
Yeah, so here, I'll just draw out the quick, like, regular scheme of what they look like. So you have group here, and so up, 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 right? Down, down, down. And those are our axial ones. And then our equatorial are just opposite. So down, up, down, up, down, up.
So say if the methyl was trans instead, then it would be axial instead of equatorial.
Yes, it would have been axial and up. Well, because it needed to be up, yeah. Make sense? So that's like the scheme you'll always follow of where the substituents go, if they're axial or equatorial. So then, what about for this one? Okay. Is that tert-butyl? Okay. So, okay. Yeah, I'll just. Is this the most stable conformation? Okay. Everyone agrees? Good. Mm-hmm. So, well, they're both equatorial, right? So are you saying if they were both axial? No, that's okay. So yeah, that's something to keep in mind, are like whether they're like on the wedge and dash or wedge and wedge, that has to do with whether it's up or down, not whether it's equatorial or axial. Yeah. Exactly, yeah. So axial would be less stable, but it would still be right because they'd be on opposite. Okay?
They're both
Yeah, so equatorial is always going to be our most stable, right? All right, so our next one.
I think like this one, you like either CO and ME would both be axial or equatorial, and I think you want them both equatorial since you got CL without the other thing.
Okay, so did everyone follow that?
Can I ask you a quick question on
Yeah.
that one?
Mm-hmm.
Could both of them have been down or is up more stable?
These two?
Like, I thought you just said the dash means that they were pointing up. And we might probably want equatorial because it's more stable.
So the dash doesn't tell you anything about whether it points. Well, you can do it however, you just need them to be opposite. So you need to pick the one. The way I would do it, like drawing the chair conformations, is pick your like highest priority group, put that on an equatorial position, doesn't matter which one until you like figure it. Sometimes it'll be the case that if you put it on a down equatorial, the other one can't be on an equatorial, but if you put the first one on an up equatorial, it could be. So you just need to look at that. If that, maybe that was more confusing than necessary, but
I just thought you just said that the wedge and the dash only tells the difference between whether it's pointing up or down, not if it's equatorial or axial.
between each other. So, but yeah, it doesn't tell you, you're the one that picks whether it's equatorial or axial. We could have also drawn this one as down here and then down here. It could have been BR and then methyl. Exactly. Yeah, so that's still a chair conformation of that, but it wouldn't be the most stable one.
Okay, so I think my original question was could I have drawn them both up? And it would still be the same.
Well, let's see. So if you drawn, well, because if you drawn it here, this would be up, so BR here, and then it would be one carbon away, and this would still be up, so yeah, you could. Do you see that? Yeah. Okay, good. Yeah, there are many ways. As long as you're just looking at your equatorial. Okay. So then going on to this one. Any more questions on that at all? Okay. So for this one. Bless you. So chlorine on an equatorial. Do you guys care where? Okay. So let's do our chlorine there.
Then like far away on the the very bottom tip of the other side, then you'll draw the methyl on it going up. So it's like farthest away.
Okay.
And on either of the other ones, you can draw like how about the top one? Draw the axial as that fluid.
Like that?
Yeah.
Is this our most stable? The ethyl? Could we make that also equatorial? How? So I'll draw this here. So now I have the what? No, go for it.
I don't know how to go for it.
I'm sorry, what? Okay, well here, first let's number them. So then how would we number this? So 1, and then which way? Clockwise or counterclockwise? Clockwise. So was this right? No, right? Because, well, hold on. Oh, no, that was still right. But then, so can we make it equatorial, as someone said earlier? Make all of them equatorial. Can we make the ethyl equatorial? Would that be more stable?
Couldn't you make both ethyl and then methyl equatorial or an axial, but it wouldn't be less, it would be less stable?
Yeah, so you could do it, but it'd be less stable. You're right. So then we can do our chlorine as equatorial and then our ethyl as equatorial, making this axial, right? So which one's more stable? On the right, good.
That one's more stable?
Why is this more stable? Yeah.
Why are both chlorine and ethyl chlorine there? One has that and one not?
Thank you. So which one's more stable? Yeah, they'd be the same in this case, so ignore the circling. Okay, so is there any way that we can put the ethyl on the equatorial with the chlorine?
I don't think so.
Why not?
Because like if you look at like
Good.
this one, you got like the BR and that one, you know, they're both going the same direction, and there's like one carbon in between. Well, here there's one carbon in between, but they're going different ways, so it's always going to be different ways.
Good, yeah, so it's because of the number of carbons away from each other, you can't have them both, and because they are like pointing in opposite directions. Okay. Do you guys want to do this one or move on? Move on. So determine whether the following pairs are constitutional isomers, diastereomers, and enantiomers, or the same molecule. Okay. Good. And then how about this one? Which one? Okay. Why? Good. So two of them are changing, one's staying the same. How about this? So are they diastereomers or enantiomers? So someone shook their head. Why not? Okay, so they're basically the arrangement of the atoms is different, right? Do they?
Oh, sorry, that's the hash. Say the hash is on the bottom too.
Okay, yeah. But so do they have the same molecular formula? Good. So they're constitutional isomers. There is, but in this case it would just be constitutional isomers because they have no relation in like the bonding. So you need to look at that. Yeah. Okay. So now, yes.
You can count the longest carbon chain in the as well. With like constitutional isomers.
Like, I'm sorry, what?
I was like, can you count the longest carbon chain, or do they both have the same carbon chain?
Yeah, it's just the arrangement, like the bonding. That's different. Okay, so now on to synthesis problems. So propose an efficient synthesis for the following. For these, I'm going to rely completely on you guys. You're going to, because when it comes to the test, you're going to have to do this completely on your own. So try and look if you have your notes about, or if you have your reagents memorized already. You can work on this for a few minutes and then get back to me. I'll put it up after this, yeah. On it'll be the Study Union WordPress site. So if you look up UCF Study Union WordPress, it'll come up. Yeah, so the diastereomer, you want to look at. Are you guys working on this, or do you already know? Okay, no, that's fine. So here, I'll just show you.
For the diastereoisomer, I saw there's like one on dash, another one on wedge. Right. Oh, that's enadine now.
But then if you had this,
That's diastereo.
exactly. Because,
Only one of them can change. Like when one of the wedges becomes a dash and a dash becomes a wedge, like this right here.
so diastereomers, you need to have at least one that stays the same.
Okay. You said diastereoisomers. Okay.
Yeah.
So these both flip. So if this was like a wedge and it started off and this was a dash and this is a wedge, it'll be an anatomy. Awesome.
Isn't it, this one remain, these two change, right? And then these two change. Isn't it enadine, right?
These two did not change.
Oh, just because of that. What about, I thought you don't look at the whole thing, you just look at the first.
Oh, well, it would, but this is one molecule, so it doesn't change. So you need to look at the whole thing.
What about this one as well? Like,
They're constitutional because the bonding changes. This over here is now down here instead. So they're not the same molecule, like they're not the same.
I thought if you look at that way, and then you can look at this way, if you count this one as this one,
I see what you're saying.
it actually is like 1, 2, 3, 4, and this one is 3 and 4 as well. So these two change, just change from a dash to a line.
I see what you're saying.
Could it be
I'll fix that, yeah.
diastereo?
Yes, do you have one, the synthesis? Okay, yay! All right, what do you think? Oh. So what's our first step? Okay, and what does HBr and ROR give us? Can we come back together again, please? Sorry, it's distracting. So it adds 1 BR to where? Anti-Markovnikov, good. And why did we want to do that? Good. Could we have used, wait, NA what? Oh, any. Could we have used any elimination reaction? Could we have used NaOH? Or any, why not? Awesome, because we want our Hoffman, so we need a strong, bulky base. Okay, are we all good with this? Any questions on this synthesis? Okay. Now this one. Yeah, this is a methyl, this is an ethyl. Does anyone have an answer yet? You guys got it? Yeah. Okay. All right, so I think we have an answer. Do you guys want more time to try and figure it out yourself, or you want to just get it? Okay. So what do you guys think it is? Here, I think they had the answer here. So what do we need to do?
The first step is to take away the OH to
Okay. Is this numbered?
Yeah, figure 1 and 2.
Okay. Good. So we have, and what does this do? Double bond? Okay. And then what? What did you guys have?
And then we had plus acid catalyzed hydration with water, so H2O and H2O.
Good. Awesome. Mhm. For this double bond, what are the reagents that can eliminate an alcohol? So we need this because remember we need to like actually protonate this before it can leave. So that's why it's a like weird elimination reagent. Yes. H2SO4? Could we? Okay. To eliminate it? H2SO4 and H2O. I see that working, yeah. But for these like elimination of the OH, this will for sure give you this elimination product. Like definitely. So that's why I would stick with that when it comes to this type of problem. Does that make sense? Okay. So are we comfortable with these? And here's our next one. Does anyone have an answer yet? Okay. And how do we make sure that it comes, oh, well, wait, no, never mind. What product is this? Good. So our Markovnikov, which is how? Well, what are the reagents? Good. Yes. You had your hand up? If that would give you the Hoffman. Wait, how? Wait, can you repeat that? KOCH3? Like that, right? Oh, there's another. Okay, okay. So you're saying something like this. Like that? Okay. Why can we not use that? Bulky, yeah. So that'll be bulky, and that'll give you your Hoffman product, right? So, yeah, exactly. So that'll be, because, can anyone explain why that a bulky base would give us a Hoffman product? Awesome. Yeah, so it's too sterically hindered to go in and grab that proton that it needs to make the Zaitsev. So it needs to come out here. Make sense? Okay. Well, no, she was saying this. I just understood her wrong, so she wasn't saying this. She was saying something else, right?
Yeah, there's another C, and then in parentheses it's CH33.
CH33, right? Yeah. Okay, yes. So that's like that. That's tert butoxide. Yeah. Yeah, because this is a tert butyl, right?
Because that's what he used in his exam, so now I'm like trying to learn that one.
As what? Oh, okay. He writes it out this way? Okay, okay. So, yeah, so then to clear that up, tert butoxide is this, okay? Just dry out if you're ever confused, because that's a tert butyl. And that's an like oxide when it has the K here. Okay? Yeah, no problem. Okay, so now let me see how many. So let's go ahead and do this one. So what's the first step we need to do? You said what? Deprotonate this? Okay, to do what? Okay, so like that? Oh, sorry, hold on. Well, yeah, that is, if we eliminate, that's what we're getting, right? Yeah, so then what do we need to do? Yeah. Yeah, so we'll need to do the addition of carbons, right? Meaning we need to get what? A terminal alkyne. You said it earlier, yeah. So we need to get a terminal alkyne. How can we do that? So, well, how many carbons are we adding from here to here? 2. So we need to add 2 carbons. To what read? Okay, how? What do we do?
Or would it just be like a CH3CH2Br? That's kind of like, because the bromine's already a good lead.
Yes.
So then you need like a certain amount of carbons to make that alkyne. So wouldn't it just be like CH3CH2Br and then the 2 bromines pair up? The CH3 and CH2 attack that site?
Oh, I see what you're saying. Well, so in order to do any sort of elimination first, we know that we can't eliminate onto this bond, right? I think you were onto something earlier. We need to do, if we can't do elimination, what can we do? Okay. With what? What gives us like more options, more things to like mess around with?
We have a leaving group and like an equal. So like say if we get like BrCl ET or BrET.
So you want to just put a Cl here instead?
Would that equal?
What would that do?
I'm just trying to get like a leaving group so we can use the alpha carbon to make an alkyne.
Okay, I see what you're saying. So then, so what reagent? Cl. What if we substituted this instead? What reagent can we use?
Wait, but I'm sorry, why does it matter what PR already uses? Why aren't we just trying that on?
What can alcohol do? Like what can an OH, what kind of reactions can it do?
Use hydrogenation to protonate it or leave, but
So we know we need to add a carbon here, right? So that we can do any sort of elimination to get a terminal alkyne, right? Did you guys follow that? So I'll give you, okay. I'll give you a few more minutes. Look through your list of reagents. Try and find something that can give you another carbon added. Epoxide? So how? So do something, like what would that look like? Yes.
Couldn't you just add the acetyl group to that?
Like that?
Substitution? Yeah.
We can try that. Yeah. So let's go ahead and try what they have. That I haven't seen it that way, but okay. So they're saying to use this, an acetylene ion, as a nucleophile to then give us a substitution. Make sense? So we could do that, and then what do we need to do? Okay, so we need to add another carbon. How do we do that? Do what? So just CH3Br. Uh-huh. Yes. This one here. This reaction. Oh, I see. Oh, so you're saying to go straight from here to here. Oh, okay. Yeah, I've never seen that, but
I think it's on like some practice tests we looked up.
oh, okay.
It makes sense.
Yes. Well, because you're adding, yeah, I see what you're saying. You're adding 2 carbons in that case, because you have this as your nucleophile. This leaves, this comes in here. But then, yeah. The way, okay, so we're almost out of time, so I'll post the answer that I was thinking on there so that we can like actually get to some like IR. Do you guys want to do IR? Okay, cool. So what functional groups or group are shown here? Is this a carboxylic acid? Why not? What are we missing? A what? Good. So the carboxylic acid peak includes this peak in it, right? So it has a little, it would look something like that, because it has both of them included. Does that make sense? So this, no? Okay. Where? In here? Mm-hmm. Yeah. So this will just be an OH, right? And then what do we have here? Yeah, the functional group.
So that's 3,000. We have it could be an alkene or alkene.
What's the like peak of interest here? The what? What is this? This one here. Yeah, so that's CSP3H. Does that tell us anything? No, right? Because basically everything that we work with has that. So what's our peak of interest? This one. And that tells us what? Amine? What kind of amine? Secondary? Do y'all agree? What would it be? So what is, oh, I wonder if you can see it. Okay, can I zoom out? Oh, it's, okay. So can you see the difference between the top one and the bottom one?
Yes.
What is this?
Secondary?
Secondary? Okay. So this would be also an amine, right? Why would it be secondary?
It's got a point here.
So this would be primary?
Yeah.
So in IR, the way that it works, what does the primary amine look like? How many R groups? One R, and then 2 H's, right? So these H's are what's making, this like NH bond is what's making the little blip. Because anything up here, remember, is like anything bonded to H. So that is like what the little blip is doing. It's that there's 2. Mm-hmm. Yeah. And then finally this one. Good. Awesome. All right. So that is the end of the review. I will be posting, oh, I also have a match each compound with the appropriate IR. I'll post the answers. Well, I'll post like this first so you guys can work on it, and then I'll post the answers. I do real quick have a little survey that if you guys could just fill out super quickly. It'll be the number 43 is the one that you need to bubble in at the top.